All right, we have been studying Fourier series of periodic functions with a period of 2 pi only. So a natural question to ask is what happens if the period is not 2 pi? So let's say if we have a function of period of 2 pi L, well, L is any positive real number, okay? Then we can define the Fourier series of function f as this. K from negative infinity to positive infinity, and ck is a Fourier coefficient, an exponential of k ikx divided by L. And of course, ck is the Fourier coefficient, and in this case, we define it as 2 pi, 1 over 2 pi L instead of 2 pi, and integrate from negative L pi to L pi. And the function f of x times exponential of negative ikx over L dx. And if we assume f of x is continuously differentiable, then this is actually equal. So in this way, Fourier series can be extended to any periodic functions, not just or with period of 2 pi, but any period. So why does this work? This is just a method of scaling the coordinate system. So if we set y equals to x over L, then replace everything here with y, then we have s of, let's say f of x is f of ly. Let's define this as g of y. Okay, so the Fourier series of g is this ck and iky. So this is the Fourier series we have been studying all the way for the period for the functions with period of 2 pi. And in fact, this function g of y has a period of 2 pi because x has f of x has period of 2 pi L, and if we divide that by L, then this function of y has a period of 2 pi. So all of the properties we have proved about the Fourier series for the functions with a period of 2 pi are applicable to functions of any period. Just in case you're wondering what happens to the Fourier coefficient if we replace x with y. So from here we have dy equals to dx over L. So this L and this dx will be replaced with dy, and this will be y. So that is the Fourier coefficient we have. So L pi becomes pi, right? Negative pi, 2 pi, and g of y, and exponential of negative iky dy. So this coefficient is this coefficient, and they are the same, and this expression is the same as we have been studying. So everything is fine. All right, the next question is, what about non-periodic functions? Here we consider a class of functions that are continuously differentiable with bounded support. Support means the set. Support of f is the set, in this case real numbers, such that f of x is not equal to 0. So this is the support, definition of the support, and bounded support means this. So support of f is a subset of some, let's say, uh, constant interval, negative L pi to L pi. Okay, L is any positive real number. Okay, so this support is bounded by this interval. For example, let's try to plot some function. So since this is bounded, so if L is large enough, then all the values of f is 0. Okay, 0. And within some interval, it can take non-zero values. Okay, so this is an example of a function with a bounded support. Now let's calculate the Fourier coefficient of this such function. So ck is 1 over 2 pi L and negative L pi and L pi. Okay, just regarding this function as just pretend this function to be a periodic function with a period of L pi, L to L pi. So we integrate from negative L pi to positive L pi and multiply f of x with exponential of negative I k x over L and dx. Now, since the support is bounded by this, so if we extend these limits to negative or positive infinities, then the integral doesn't change. So we replace with plus minus infinities here. And next, let's define a new function f hat of xi as 1 over square root of 2 pi and integral from negative infinity to positive infinity f of x exponential of negative I xi x dx, where xi is a real variable. Okay, using this, we can express this Fourier coefficient ck as ck is equal to 1 over 2 square root of 2 pi and f hat of wait a minute, k over L and 1 over L. Okay, so this L comes here, and we have 2 pi here in the denominator, so let's take square root of it, and one of the square roots comes here and the other remains here, and this xi is k over L. Okay, so this is an expression of the Fourier coefficient ck in terms of f hat. So now, since we're assuming that the function f is smooth or continuously differentiable, f of x can be expressed as the Fourier series ck and exponential of I k x over L. Okay, now replace this ck with this expression. Okay, then we have 1 over square root of 2 pi and f hat k over L and exponential I, let's write I k over L x and 1 over L. Okay, now let's set xi k as k over L. Then we have xi k plus 1 minus xi k is 1 over L. Okay, So let's write this as delta xi k. Okay, so this becomes 2 pi and summation and f hat psi k and exponential of I psi kx and delta psi k. So this is, can you recognize any pattern? This is a Riemann sum. So if we take the limit L going to infinity, this sum converges to the Riemann integral. Negative infinity to positive infinity, f hat xi exponential of I xi x and d xi. So to summarize, we have f of x represented as a linear combination of infinitely many functions of this form with coefficients of f hat, where f hat xi is this f of x exponential of psi x dx. So this is a generalization of the Fourier series to non-periodic functions or any functions in general. And this is called Fourier transform of f. Oh, this one is Fourier transform, and this one is called the inversion formula. So given a function f, we can calculate its Fourier transform f hat, and from f hat, we can revert the original function f of x using the inverse Fourier transform. Okay, that's it. The further study of Fourier transform is beyond the scope of this lecture, so we stop here. And that's the end of the lecture series on mathematical methods 2. Okay, bye.